which we already saw now at the last step. Step 2 is the selection of displacement function, shape function or the displacement functions, which we defined, which we used for defining, which we use for the corresponding element is u, and we know the nodal displacements to become to be u1 and u2, and the relationship is given by the shape functions. When we substitute a particular, when a particular coordinate of the point is substituted to this n of this equation, it gives the displacement of a point, of course, within the element, or using the nodal coordinates, nodal degrees of freedom u1 in u2. So because the function u, that is the displacement, nodal displacement, and of course x, which defines the shape of the element, are functions of the same nodes, or these are functions of the s value. You can see it by comparing, let's say, equation 7.16 and of course the equation 7.14, the x and u, the displacement, the x, the shape, and u, the displacements functions are expressed using the same parameter. So because of this, we call it an isoparametric formulation. They are expressed using shape functions, and the shape functions are described using the natural coordinate systems, that is S. So because of that reason, we call this an isoparametric formulation. So what is the next step? The next logical step in deriving the element stiffness matrix, of course, is to define the strain displacement as well as to find the relationship between the stresses and strains. So this links the displacements of the nodal degrees of freedom to the, let's say, forces acting on the element. So the next step is defining the strain displacement or stress strain relationship. So because this is the first step, because we have used simple model, a simple, let's say, uniaxial bar element to apply the isoparametric formulations. I will be going through the steps quite slowly, in a step-by-step manner. And in the next step, when we look at, let's say, a plane stress element, let's say kind of like a rectangular element, I will quickly go through the steps because we have already dealt with what is necessary in this step. So that is why I'm taking time to go through each of these steps. We are now trying to relate the displacements to the forces via the stress strain relationships, and of course strain displacement relationship. So what is the intention? We want to, let's say, in order to find the element stiffness matrix, we need to find the element matrix, that is the B matrix. We need to find, in order to find the element stiffness matrix, we require to find the element matrix, which is B matrix, which is described using the global coordinate system. Of course, in this case, we are using a simple same parameter, that is, we are using the natural coordinate system to express this element. How can we construct the element stiffness matrix? In order to construct this element stiffness matrix, we need to define, we need to calculate the strain, which is determined, of course, using the derivatives with respect to x. We know the displacement or the strain is defined using the displacements, and of course using the derivative of the displacement with respect to x. And we know now the displacement u is a function of, let's say, the natural coordinate system, that is S. So we need to find a relationship to express this strains in the new coordinate system. So for that, we need to, let's say, in order to find the relationship between the displacement and the strains, we need to obtain this derivative, isn't it? Du by dx. But we know that u is not directly expressed as a function of x now. It is expressed as a function of s. So in order to find this derivative, we need to apply the chain rule, yeah, for the differentiation. So what we require is du by ds, and for this, what we do is we apply the chain rule. Since we cannot differentiate with respect to, of course, x, what we do is we apply the chain rule, that is express du by dx, derivative of displacement with respect to the natural coordinate system, by applying the chain rule du by dx times dx times ds. So we have applied the chain rule. So since we can evaluate du by ds, and of course dx by ds, because we already know the relationship between the terms u and s, the displacements x and s, of course, with this equation, if you can remember, the u and s relationships are defined in this equation, of course, wherever we have the shape, because the shape functions are described in the natural coordinate system. And in equation 7.1.4, the x displacements are also again described using s in the s coordinate system. So we are able to evaluate these two derivatives, du by ds and dx by ds, of course. Because of this, we are now interested in calculating the du by dx, which gives us the strain in the x direction. So this, we are interested in calculating du by dx. So because of this, with this intention, let's try to express du by dx, which we would like to access the strain, and it is nothing but the ratio between these two derivatives. Using this equation 0.1.7, you can see that it is nothing but the derivative of this ratio of these two derivatives. Let's call it 7.1.8. Using this equation 7.1.6, which describes the relationship between the displacement, nodal displacement, and the shape functions or its coordinate system, one can find du by ds. Using 7.1.6, you will be able to calculate du by ds, and when you solve this, you would get du by ds is equal to u2 minus u1 divided by 2. Let's call it 7.1.98. Right. So using equation, of course, 7.1.4, of course 7.1.3, because this express there's a function which relates provides the relationship between the two coordinate systems. Using 7.1.3, you are able to find the relationship or obtain the derivative dx by ds, and it is simply a function of the two nodal coordinates, and we know the x2 minus x1 is equal to L in this case, because the length of the bar element is L. So let's call it 7.1.9b. Combining this equation 7.1.9a and 7.9.b, we can write down the equation for the strain in the x direction, yeah, simply by substituting the du by ds and dx by ds value into this equation 7.1.8, we will be able to obtain the strain in the x direction. So the strain, so by using 7.1.9a and 7.1.9b, we will be able to express the strain, which is of course two elements, as a function of u1 and u2. You can solve it on your own to obtain the following relationship. Since we already know this the displacement, okay, the relationship between the strain and the displacement here is given by this B matrix. Now we can say a B matrix, the element matrix, is equal to 1 minus L divided by, and the other term is 1 minus L. Next, since we have already found the B matrix, we can now use the Hooke's law to relate it to the stressors. The strain, we can relate the strain to the stressors by applying Hooke's law. We know that the stresses are related to strains where the modulus of elasticity, and since we already know the strain is now equal to the element matrix times the displacement matrix, we have a relationship between the stressors and the strains. Now the next step is step 4, to derive the element stiffness matrix and of course the corresponding equations. So let's write down the step 4 as deriving the element stiffness matrix. We know the element stiffness matrix is a function of the element matrix B, the constitutive matrix which contains all the properties, and of course Wave matrix and the geometric relationships. Of course we remember, I hope you can remember, and in order to evaluate this matrix we need to find the integral between 0 to L. And now what we need to do is, since we are operating in a new coordinate system, in the natural coordinate system, and in order to we need to transform the x coordinate to s coordinate in order to evaluate this integral, because the B matrix, of course, in general, is a function of S. Yeah. Since we have used only a linear relationship, or let's say linear shape functions, of course, we get to constant strain within the element. But if we use high order shape functions, of course, if we use, let's say, quadratic terms, higher order elements such as, let's say, quadratic bar having more nodes, say 3 nodes, this B matrix will become a function of S. So of course, since it's a linear function, we get 2 constants. So yeah, but the general principle is, if we are now using the isoparametric formulation, we have to convert the 2 coordinate system. That is, because B is expressed in terms of S, we need to do a transformation of the 2 reference frames. The transformation from the x coordinate system to s coordinate system is given by the following relationship. So we need to transform this integral from 0 to L, and if we have a function from function fx, and we need to evaluate the integral, and the corresponding function which is bounded by -1 and 1, of course, described in the using the natural coordinate system, is given by multiplying with the Jacobian, the modulus of the Jacobian. So here J is called the Jacobian matrix. Of course, it's a modulus. Now we have to get the, let's say, modulus value, of course, of this Jacobian matrix. And in the case of one-dimensional problem, since we use a one-dimensional bar element, the modulus, of course, is also equal to J for the simple bar element. And from this equation, let's say 7.1.9b, we can say the modulus of the Jacobian is, that is, dx by ds is equal to nothing but L by 2. Let's call it 7.12, 13. So in general, this Jacobian, the modulus of Jacobian is a function of the natural coordinate system. And of course, uh, it it depends on the numerical values of the nodal coordinates. So this would be quite visible when we look at, let's say, higher order elements, let's say if the time permits, of course. And if you would like to, I mean, how to evaluate the Jacobian, you can, maybe you have already learned probably during your controls lecture, or you can also refer to, let's say, reference material to see how you can evaluate the Jacobian of a matrix using, let's say, the equations which we just derived. Let's say we can now express the element stiffness matrix. We can use equation, let's say 7.1.13, that is this equation, the transformation, of course, and 7.1.14. We can use this equation in the expression which provides the value, of course, the expression for the stiffness matrix, element stiffness matrix. We can substitute the corresponding values in 7.1.12 to obtain the element stiffness matrix for the element, of course, linear bar element in the natural coordinate system. This is bounded by 1 and -1, and of course we have the element matrix, the transpose of the element matrix. We have a modulus of elasticity in the place of D, in the place of constitutive matrix, times B, and of course S. We see for a one-dimensional, let's say, bar element, the modulus of elasticity will become equal, of course, to the constitutive matrix in the case of 1D element. So if we evaluate, if we substitute the corresponding values for this B, that is the B matrices which we evaluated, if we substitute these values from 7.1.11 in order to find the elements matrix in this equation and do the integral and solve the integral, so you can substitute these values from 7.1.11 and you do the evaluate, and when you evaluate the integral, interestingly, you would end up getting the element stiffness matrix which you derived the previous session using the global coordinate system. Of course, you would end up in getting the same relationship which you derived previously in the previous chapters. Yeah, so meaning by even applying the isoparametric formulation, you end up in getting the same result. For, let's say, for higher order, let's say one-dimensional elements, of course, this evaluation of this integral becomes really cumbersome. It's become really difficult. And even for the simplest case of, let's say, rectangular element, which we will consider in the next step, the evaluation of this closed form integral will become difficult. So we need to resort to, or we need to use numerical schemes or numerical integration schemes, which we will also be describing in the later sections or in the coming lectures. And we can use such numerical integration schemes in order to evaluate such integrals, because we are interested in solving these element stiffness matrices, of course, complex high order elements and for large number of elements. These numerical integration schemes will become quite handy, especially coupled with the isoparametric formulations, and it would be quite handy because it will be quite easy for implementing procedural computer programs when you are solving the finite element problems. So having said that, now I think I have motivated you that this method is quite, let's say, powerful, and it of course this is not directly straightforward using this example because this is too simple, but maybe in the next step when we move on to let's say analyzing a rectangular plane stress element, the performance of system would be quite evident to you all, especially when we talk in terms of curved surfaces and edges, skewed edges. This method, so you see that using even this method, we are able to obtain the same result which we obtained using the displacement method using global coordinate system. Just before we move on to, let's say, discuss about rectangular plane stress element, I would like to quickly highlight about the body forces and also the surface forces, how we can apply, how we can relate the body forces and the surface forces acting on a certain element, and how the computer deals with such problems via the shape functions is of importance in this problem. So before we move on to deriving, let's say, before we move on to focus on a slightly complicated problem, that is, before discussing a rectangular plane stress element, where we will be discussing where we'll be deriving the element stiffness matrix using the global coordinate system, and also we will be applying the isoparametric formulation to see what we get, whether we end up in the same result. We will quickly go through how we can define the body forces and the surface forces acting on a certain element.